Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 4. In the last lecture, we studied free and force vibrations of single degree of freedom undamped systems. In practice, however, systems dissipate energy when they vibrate, and this dissipation affects the free and force response of the system. So, in this lecture today, we are going to study the free and force vibrations of single degree of freedom systems with viscous damping. So, today's topic is free and forced vibration of single degree of freedom systems with viscous damping. Right. So, that is nothing but the topic we are going to study today. What is damping? So, systems have some mechanisms through which they dissipate energy of the system, and damping refers to all such mechanisms which exist in the system, right. So, damping refers to dissipation of energy in the system, dissipation of energy of the system, right. That is nothing but damping, and such dissipation may occur because of several reasons. For example, there may be viscous friction, right, which may occur if there are the system while vibrating is subjected to forces due to fluids, gases and so on, right. So, they generate viscous forces which tend to resist the motion of the system, and in the process they dissipate energy of the system. Then there could be dry friction, right, which is referred as Coulomb damping. So, again if there is dry friction, that is then again the friction forces they do work against the motion of the body, right, and in the process they dissipate energy. Viscous friction, of course, can be referred as or is referred as viscous damping. Then there may be dissipation of energy due to hysteresis effect. Often referred as structural damping. Okay, so that I think we will study more later. Then there could be some other internal mechanisms, some other mechanisms internal to the body, which again may cause dissipation. There is also something called acoustic damping. Because when a body or system vibrates, it also radiates sound, right, and therefore the energy of the system is also partially dissipated away through the propagation of sound, So, that is referred to acoustic damping. So, these are the sources through which the energy of the system may be dissipated, and all of them are referred as sources of damping. But in practice, we often use a viscous damping model. We often use a viscous damping model in the form of a viscous dashpot to represent energy dissipation in the system. So, irrespective of the actual mechanisms that are present and which are responsible for dissipation of energy, we may use a viscous damping model to represent the damping in the system, right. And this is because the viscous damping model offers ease in the mathematical analysis of the system. Okay. So, this offers ease in the mathematical analysis. Okay. So, viscous dashpot is represented by a piston like this, a piston which is moving in a cylinder filled with oil. Okay. So, this is nothing but viscous dashpot, and so if we plot the force of resistance of this then it is proportional to the velocity, the relative velocity between the two ends of the damper, right. So, this is nothing but the force of resistance of the viscous dashpot, and F is proportional to velocity, and the constant of proportionality is C, which is referred as viscous damping coefficient. Damping coefficient, and it has units Newton per meter per second, right. So, the force of resistance, right, per unit velocity, relative velocity between its ends. So, therefore, first now we are going to study the free vibration. Okay. So, we are going to study the free vibration of a single degree of freedom system with viscous damping, and therefore, let us sketch the system. Maybe we can show it like this. Okay. So, that is mass, stiffness and damping. I would like to emphasize that this is a single degree of freedom system, but actually it is a single degree of freedom model of a practical system, right. So, any practical system we have modeled it through a single degree of freedom model, and this system we are referring as single degree of freedom system with viscous damping. So, now we would like to write equations of motion and then analyze the free vibration characteristics of the system. So, let us say this is the the static equilibrium position, right. Let us say this is the static equilibrium position, with respect to which we are going to measure the vibration of the system, right. So, let us say the system is displaced by a displacement x like this. Okay. So, that is nothing but the displacement of the system, and then we would like to draw the free body diagram in this condition of the mass, right. So, the Kx is going to be the force due to spring, and we will have Cx dot as the force due to damper, and this mass has an acceleration of x double dot at this position. Okay. So, now we are in a position to apply the relevant physical law here in order to write the equation of motion. So, if you apply Newton's law, which says that the mass into acceleration is equal to summation of algebraic summation of all the forces which are acting on the system, right. So, since the force due to spring and force due to damper, they act opposite to the acceleration, we take them as negative. So, mx double dot is equal to minus kx plus minus cx dot, right, and then we have mx double dot plus cx dot plus kx is equal to 0. So, that is nothing but the equation of motion, right. See, nothing but the equation of motion. Okay. So, now we would like to solve this differential equation. It is a second order differential equation, a linear equation of second order. We would like to solve this equation. So, we note that here we have an additional force term Cx dot, which is proportional to velocity, and because of that this equation does not represent simple harmonic motion. Okay, it does not represent simple harmonic motion, because in the simple harmonic motion the acceleration has to be proportional to only displacement, right. So, therefore, the solutions we assume in the undamped case, right, like A cos omega t or B sin omega t, those solutions no longer will be in the solutions of this differential equation. So, physically speaking, under the free vibration, what is going to happen is that the displacement of the mass would gradually decay with time, because the energy of the system would be dissipated by the damping forces. And therefore, we require a mathematical solution which can capture this decaying nature of the displacement, and hence we assume a solution which has the ability to model decay of vibration. So, let us assume x of t as say a e to the power s t. Okay. Here s is a complex number. Okay, it is a complex quantity. Okay. So, if this has to be the solution of the differential equation, it must satisfy the differential equation, and hence we substitute this into the differential equation. When we do that and we do the necessary algebraic we do the differentiation, then what do you get? We get s square e to the power s t a s e to the power s t plus k a e to the power s t is equal to 0, which means ms square plus c s plus k e to the power s t, right, also a is equal to 0, correct. So, now here a into e to the power s t cannot be 0, right, because if that is 0, then the displacement of the mass is also 0, because that is the solution we assume, and that would not reflect the vibratory nature or vibratory motion of the system, and hence it cannot be a valid solution. It is not a solution of the system, and hence the other way this equation can satisfy is when ms square plus cs plus k is equal to 0. So, if that is 0, then also the solution a into e to the power s t would satisfy the differential equation. Let us write that again. So, the equation we have ms square plus cs plus k is equal to 0. So, S12 would be minus c plus minus under root of square minus 4 a k m upon 2m, right. So, that is going to be the relationship. So, this is I think the correct formula, right. So, therefore, the general solution the general solution is given by a linear combination of two solutions. So, one solution is you know A1 e to the power S1t and other solution is A2 e to the power S2t. So, a linear combination of these two solutions gives us the general solution. So, the nature of X solution depends on nature of S1 and S2, right. So, the nature of X depends on nature of S1 and S2, right, and the nature of S1 S2 depends on the sign of the this term in the square root c square minus 4m, phi square minus 4km, and depending upon whether c square is more than 4km or less than 4km would determine the nature of the root, and hence the boundary between the transition from say a positive value of c square minus 4km to a negative value of c square minus 4m, that transition is decided by the value which makes c square equal to 4km, right. So, therefore, if we say c square is equal to 4km, right. So, so what is the damping coefficient which makes this equation satisfy, right, that is c square is equal to 4km. Let us determine that damping. So, that would be nothing but 2 under root km, okay. So, when the damping in the system, the viscous damping coefficient of the system, it is equal to 2 under root km, then this c square minus 4km would be equal to 0, right, and such a damping and that would make the two roots S1 S2 equal, okay. So, such a damping coefficient in the system is referred as critical value of the damping in the system, right, and hence we say that Cc is equal to 2 under root km, where Cc represents critical damping coefficient. So, this is nothing but the critical damping coefficient, and then we define a non-dimensional factor to quantify damping. We define a non-dimensional factor to quantify damping in the system, right. And that we define as the ratio of the actual damping coefficient and the critical value of the damping coefficient. So, we that refer as damping factor C upon Cc. This is referred as, this is called as damping factor or viscous damping factor, okay, and is the ratio of the actual damping coefficient which exists in the system to the critical value of the damping coefficient. Right. So, let us now rewrite these roots in the form of damping factor and natural frequency of the system. So, we have S12 is equal to minus C plus minus under root of C square minus 4km divided by 2m, and this we can write as minus C upon 2m plus minus, right. If we take 2m inside the square root, we get C by 2m square minus 4km upon 4m square, right. So, that makes it k by m. So, if we look one by one at these factors, then C by 2m can be written as Cc times damping factor, right, and Cc can be written as 2 under root km, okay, and that becomes zeta under root k by m, right, and under root k by m is nothing but the natural frequency of the system. So, this gives zeta omega n. So, C by 2m is nothing but zeta omega n, and k by m is nothing but omega n square, and hence we get S12 as minus zeta omega n plus minus zeta square omega n square minus omega n square. So, k by m is nothing but omega n square, and therefore, we can write this as minus zeta plus minus under root of zeta square minus 1 times omega n, right. So, we see that the two roots of the complex roots of the system, they depend on the damping factor and the natural frequency. And now, depending upon whether the damping factor zeta is more than 1, less than 1 or equal to 1, the nature of the roots would be determined. So, therefore, we have these three cases, and let us study these cases one by one. So, we first of all take the case of zeta more than 1, right, and this is referred as overdamped system. Because the damping in the system is more than the critical value of the damping. Now, in this case the roots would be S1 and S2, these roots would be real and unequal, right. Roots would be real and unequal because zeta square minus 1 is positive. So, the general solution will be given by x of t. If I take zeta omega n t common, then it is minus zeta omega n t a1 e to the power plus under root of zeta square minus 1 omega n t plus a2 e to the power minus zeta square minus 1 omega n t. So, this is the general solution, and then the a1 and a2 are arbitrary constants. A1 and A2 are arbitrary constants and they depend upon the initial conditions. They depend on the initial conditions on the displacement and velocity of the mass of the system. So, if we plot say the response of the system, then it is going to look something like this. The response of the system, let us say if we take initial conditions as at t is equal to 0, x of t is equal to x naught, right, and the velocity x dot t is equal to v naught, right. So, if you take let us say a certain value of x naught, so let us plot x here and t here. So, the x of t, let us say if the velocity v naught is 0, then this is going to decay like this. And if let us say, so this for this you can see velocity is 0 and the displacement starts from x naught. If v naught is positive, then this profile may look like this, something like this. And if velocity, so this is velocity more than 0, and if the velocity is negative, then it may take this kind of shape. Okay, so this is v naught less than 0. So, you can see the system basically the displacement decays with time, and depending upon the combination of initial displacement velocity, different shapes of these curves are possible. But one characteristic is common, that the displacement decays exponentially with time, and it does not oscillate. There are no oscillations in the system, right. So, we have decay of or exponential decay of the vibration, right. The displacement of vibration decays exponentially with time, and there are no oscillations. So, in fact, it is it's it's not exactly vibration, because it is just displacement is just decaying with time. It does not cross the repeatedly the mean position, right. At most it may cross once the mean position, depending upon if the velocity is negative, right, it crosses, but otherwise it does not cross repeatedly the mean position, and hence that way it is not, there are no oscillations. So, that is the overdamped system, right. If zeta is equal to 1, right, then this is called a critically damped system. And in this case, the roots S1 and S2 are real and equal. The roots are real and equal, and and they are simply equal to S1 is equal to S2 is equal to minus zeta omega n, that is all. And therefore, the general solution is given by x of t is equal to A1 plus A2 t e to the power minus zeta omega n t. So, in this case we note that not only A1 e to the power minus zeta omega n t satisfies the differential equation, but A2 into t e to the power minus zeta omega n t also satisfies the differential equation, and that makes the general solution, right. So, simply adding A1 e to the power minus zeta omega n t and A2 e to the power minus zeta omega n t would not make up a general solution, because then we can combine both the terms and then we end up with only one arbitrary constant in the solution, and that would not represent the general solution, simply because the system or the differential equation is of second order, and then there should be two independent arbitrary constants in the solution in order for the solution to represent the general solution. So, this is the general solution, but again in this case we note that because of the presence of this term, right, e to the power minus zeta omega n t, the displacement is going to decay exponentially with time. As time t increases, because of this factor e to the power minus zeta omega n t, the displacement will reduce exponentially with time. Okay. So, if you plot again the displacement is a function of time, it is going to look something like this. So, theoretically it takes infinite time for the displacement to reach mean position 0, right. But in practice, in addition to the viscous damping which might be there, there may be other damping mechanisms which might be present, because of them, because of which the system would come to the rest or the mean position in a finite time. So, here also again we observe that there are no oscillations, right, and the response decays exponentially. With time. Let us now look at the third case where zeta is less than 1, and this case is called as a case of underdamped system. This is nothing but underdamped system. So, in this case, what is going to happen if you look at the roots S1, S2, then the roots are minus zeta plus minus under root of zeta square minus 1 omega n, right. So, in this case, because zeta is less than 1, zeta square minus 1 is negative, which makes this square root zeta square minus 1 as a complex quantity, and therefore, we can write this as minus zeta plus minus I under root of 1 minus zeta square omega n. That is how we can write down. So, now therefore, the roots are complex conjugate, right, because S2 can be written as complex conjugate of S1. So, if S1 is minus zeta plus I under root of 1 minus zeta square omega n, then S2 is simply minus zeta minus I under root of 1 minus zeta square omega n, right. So, only the sign of the imaginary part is different in the two roots, the sign of real part is same, and hence they are complex conjugate. So, in this case, if we now write the general solution, then the general solution is given by A1 e to the power S1t, right. So, we can then write minus zeta plus I under root of 1 minus zeta square omega n plus A2 e to the power minus zeta minus I under root of 1 minus zeta square omega n. Of course, I am missing t here, t. Okay. So, that is nothing but the general solution, and I can take e to the power minus zeta omega n t common, and then I am left with A1 e to the power I under root of 1 minus zeta square omega n t plus A2 e to the power minus I under root of 1 minus zeta square omega n t. Okay. So, now I can use Euler's identity, and then which says that e to the power I theta is equal to cos theta plus or maybe I can write here plus minus, right, e to the power I plus minus I theta is equal to cos theta plus minus I sin theta, correct. So, if I use that Euler's identity, then I can simplify this equation, and then let us write the simplified equation. So, using the Euler's identity, what I am going to get, I would have a cos term. Let me write down first cos term, cos under root of 1 minus zeta square omega n t, right. So, then I have here A1, so I would have A1 plus A2, right. That is what I would get from the term from the other from the e to the power minus I theta, and then I have plus A1 plus A1 minus A2, right. I sin under root of 1 minus zeta square omega n t, right, and then also I have the factor e to the power minus zeta omega n t, right. Let us check it is correct or not. So, e to the power I theta was cos theta plus I sin theta. So, I think it looks right. So, now so this is what we are getting, right, and if the vibration x of t is real, right, So, if the system is vibrating, the displacement of the system has to be real quantity, and for that thing to happen, the A1 and A2, right, they have to be complex conjugate. Then constants, arbitrary constants A1 and A2 have to be complex conjugate. Because then only the right hand side of this equation would yield a real quantity, right. And so, A1 and A2 would be complex conjugate of each other. So, when they are complex conjugate, A1 plus A2 would be a real number, right, because the imaginary parts would cancel out, and then let us represent that as some constant d, right. And similarly, the A1 minus A2 into I would again be a real number, because A1 minus A2 would lead to a imaginary number, and that multiplied by I would be a real number. So, let us represent that by another constant E. If we do that, then the general solution can be written as x of t d cos under root of 1 minus zeta square omega n t, right, plus E times sine under root of 1 minus zeta square omega n t, right, multiplied by e to the power minus zeta omega n t. Okay. And then using trigonometry, we can also now combine these cos and sine terms, right. They have the same, I mean the argument, right. So, we can combine these two quantities using trigonometry, and we can then rewrite this equation in this form: A cos zeta omega n square t minus phi, right, and into so let me add e to the power minus zeta omega n t in the beginning. So, we will have so that is nothing but the solution we get, general solution. So, here A and phi, they are arbitrary constants, and they depend on initial conditions. So, we can find them if we are given the initial conditions. Okay. So, we need two initial conditions here, and from them then we can apply those conditions to this equation, and then we will get two equations from which whose solution would lead to A and phi. Let us try to now interpret what this solution represents. This represents that the amplitude, so if you look at this part, this is the amplitude of the vibration, right, amplitude of displacement, and this is basically a function which decays exponentially, whose value reduces exponentially with time, because in the exponent we have the minus zeta omega n t, and for a time t is positive. So, hence and zeta and omega n are positive for the system, and hence the exponential this term is going to decay with time. So, we are going to have an exponential decay. So, we have exponential decay of amplitude. The second thing is that if we look at this one, this quantity is a cosine term, right. So, it represents oscillations, because cos and sine term, they are oscillatory and they represent oscillations, and the frequency of the oscillation is given by the coefficient of time t. So, whatever is the coefficient of time t, that represents the frequency of the oscillation in radians per second, right. So, therefore, we see that there are oscillations, right, vibration is there, and then the frequency of oscillation is nothing but the coefficient of t, in which in this case is under root 1 minus zeta square omega n, right. And because the system is oscillating under damped state, the system is damped, we also often called it as omega d, that is the frequency of damped oscillations, and hence we represent it as omega d. Okay. So, the damped frequency of oscillation, it depends on the natural frequency of the system omega n and the damping factor zeta of the system, and of course, it has the units radians per second. The third thing we see is that we have this phi here, right. This phi represents phase lag. So, this phi, it represents phase lag, which means that the system response, right, it reaches to the maximum value with some time lag with respect to the origin. When the vibration was started, the system maximum response has a time lag, it does not reach to the maximum at the same instant, it reaches little bit late, and that is being quantified by this phase angle phi, and of course, its units are radians, right. So, this is nothing but the how this solution can be interpreted. Let us try to sketch this. So, if you show the displacement on the y axis and time on the x axis, then this is going to look something like this. Something like this, right, and this is for a certain value of zeta, right. So, if you increase the value of zeta, then the curve would change in this manner. If you increase the value of zeta, then it may be something like this. So, this is the damped free vibration response for a higher zeta, and this is for a lower zeta. I am sorry, I have written the opposite. Now, this is lower zeta, and this is higher zeta. Okay. So, if you increase the damping, the rate at which the displacement reduces or decays, that increases. So, there is a faster decay of amplitude when the zeta increases, right, for an underdamped system. So, of course, if there is no damping, then the oscillations are going to continue forever, right, like this. They would not decay, and the amplitude of the oscillation would stay constant, like this. There is no decay, you can see there is no decay here, but in this case you can see there is decay, the amplitude is decaying with time, and that this is an exponential decay. This envelope of amplitudes is an exponential curve. Here also, that is an exponential decay.